What if Earth's magnetic field suddenly vanished? No shield, no warning, just pure cosmic chaos. Would satellites crash? Would we survive? Or is this the beginning of Earth's slow death? Imagine waking up one morning and finding out your GPS can't find your location, planes are flying blind, and your phone's signal keeps dropping for no reason. Weird, right? But what if I told you this chaos could all be triggered by something you can't see, touch, or even hear? This incredible shield, known as the Magnetosphere, is generated by powerful, dynamic forces deep inside Earth's molten outer core. It works like a spinning dynamo, creating a vast magnetic field that stretches far into space. Unlike Mercury, Venus, and Mars, Earth is surrounded by this immense magnetosphere that acts as a gatekeeper, shielding us from the constant barrage of charged particles streaming from the sun, what we call the solar wind. It also guards us against more violent threats like coronal mass ejections, which are massive clouds of solar plasma and radiation hurled through space, and cosmic rays that shoot in from distant corners of the universe. While we rarely think about it, this force field is far from simple. It flickers, it shifts, it even flips poles every few 100,000 years. So, what if one day it completely vanished? Now, scientists say that a full disappearance of Earth's magnetic field isn't likely to happen anytime soon. But let's play with that idea. Let's imagine a world with no magnetic protection. What happens to life, to our technology, to our planet itself? Recent work by researchers at Oxford and MIT offers a moment of awe and a moment of dread. In the remote Iswa supracrustal belt of Greenland, tucked beneath the ice and sheltered by stable continental crust, scientists found rocks 3.7 billion years old. These rocks are little time capsules. Iron-rich minerals locked their magnetic direction and strength into stone as they crystallized. They measured a magnetic intensity of at least 15 microteslas, half the strength we enjoy today, but close enough to call it similar. In other words, that invisible shield has been guarding us since life first took tentative hold. It wasn't just a weak safety, the Earth had a modern-style magnetic field when primitive microbes emerged. The implication? Nature takes this shield seriously. It showed up early on and has stayed, long enough and strong enough to matter. That's comforting, but it also warns us what losing it could truly mean. Because this shield wasn't a side effect, it was essential for life's survival. Fast forward to today, Earth's magnetic field is weakening overall, and one part is collapsing in real time. Over the South Atlantic and parts of South America and Africa, there's a region called the South Atlantic anomaly, a dent in Earth's shield where the magnetic field drops lower than the surrounding regions. It's not static. Over decades, the anomaly has grown, shifted westward by about 0.3 degrees per year, and may be splitting into two lobes. Satellites passing through it suffer radiation spikes, causing data corruption, electrical glitches, and even full shutdowns if not handled carefully. NASA treats it like a pothole in space. It doesn't harm you directly yet, but it shows what happens when the shield is weakened locally. But Earth's magnetic field is no stranger to change. It flips, north becomes south, and back, roughly every few 100,000 years. The last full reversal happened about 780,000 years ago when Homo erectus roamed the planet. Each flip begins with a weakening phase, sometimes followed by a brief excursion, a dip, or a wobble, but a return to normal without a full flip. These events show that even drastic changes don't instantly pull the curtain on life. Reversals are messy, but they preserve some field strength. No paleomagnetic evidence suggests the field ever vanished entirely during these flips. It weakens and shifts, but always remains. Still, if the field weakened slowly but fully faded, what would happen? With no magnetic shield, cosmic rays and solar particles would rain down more directly. On a sunny day, you'd notice nothing. But at high altitudes, airplanes, mountain peaks, and space, you'd receive a dangerous dose. Over time, UV and ionizing radiation levels at the surface would rise. Skin cancers would climb. The ozone layer could suffer. More harmful radiation would bombard electronics, leading to more malfunctions, glitches, and data errors. Even now, our magnetosphere isn't a perfect defense. Solar activity occasionally cracks open the shield, producing geomagnetic storms that can disrupt GPS, interfere with satellites, knock out power grids, and endanger astronauts. The Van Allen belts, our planet's radiation sponges, would no longer function properly, leaving Earth's surface more exposed to harmful space radiation. Though this change wouldn't render the planet instantly uninhabitable, it would raise radiation risks, make space exploration more dangerous, and dramatically alter life's balance on Earth. Then satellites rely on the magnetosphere to avoid charged particles. Without it, the entire fleet of satellites, including GPS, weather stations, and communications, would be at risk. Operators currently schedule shutdowns over the South Atlantic anomaly. Now imagine that zone spreading worldwide. Data loss, service interruptions, and a crippling ripple effect that could paralyze navigation and telecommunications. More than this, right now, we see auroras only near the poles because charged solar wind particles follow magnetic field lines. Without a field, particles would plunge into the atmosphere closer to the equator, lighting up the sky in unexpected places. It sounds dreamy, but it's a sign of the shield's collapse. And with that collapse comes something far less poetic. Earth's atmosphere wasn't smoked out despite solar wind stripping. Why? Because the magnetic field helped hold it. NASA points at planets like Mars, once protected, now a frozen wasteland with a thin atmosphere, because its field went extinct 4 billion years ago. Venus survived because of its thick atmosphere, but life there was not so much. Earth, like a turtle without its shell, would gradually lose lighter elements, hydrogen, oxygen, and eventually with time, more. It would be slow, centuries, millennia, even millions of years before things got truly bad. But a beginning would be visible, and the spectrum of blue water and oxygen-rich air would start to shift. But Earth might limp through without a full reversal into empty space. Life would adapt, slowly, painfully. High-dose radiation zones might become the new normal. People wear better shielding at high altitudes or don't go. Satellites are buried in armor or phased out. Agriculture might shift indoors to avoid cosmic assault. It would be a difficult transition, but not immediate extinction. Think less doomsday and more careful recovery. But that depends on how fast the field disappears. A rapid loss over centuries could overwhelm our adaptive abilities. A slow fade over thousands of years could give us time to adjust. That's the narrow path between catastrophe and resilience. Scientists are using global satellite missions like ESA's Swarm and NASA's monitoring tools to track the weakening field and the SAA's growth. Computer models combine mantle and core flows, mapping future drift, splits, and reversals. But there's still uncertainty. We don't know if the SAA is just a phase in a normal reversal, or the beginning of something more dramatic. Meanwhile, ancient rocks from Greenland, Canada, South Africa, and Australia hold clues to earlier field behavior, ran and waned, fluctuated and flipped. New studies underway may reveal if past excursions ever nearly extinguished the field, and how Earth recovered. So, could Earth ever completely lose its magnetic field? Today, it's extremely unlikely. The geodynamo still hums, the inner core still grows about 1 millimeter per year, and the engine hasn't sputtered in 3.7 billion years. There's no sign the core is about to stop or that heat flow will collapse. But there's a scenario where it might. If convection slows or the inner core reaches a size where buoyancy stalls, the dynamo could fade. That could take billions of years, well after humans are gone. But if we're watching now, we're watching the earliest whispers of structural change. The real danger, right now, is the South Atlantic anomaly. It's the first hole in the shield, and it's growing. Satellites are already rebooting as they cross it. Space tourism, growing each year, will carry more humans through it. Airlines may need new flight routes. Hospitals reliant on satellite timing, they'll need guard systems, and soon GPS-guided cars and drones will feel the same pinch. But humans are inventive. We can build better shields, stronger instruments, change flight paths, and redesign infrastructure. It's expensive and inconvenient, but doable. This is the moment where prevention becomes action. Will the anomaly stay contained, evolving into a known, manageable risk? Or is it the first small sign of a broader collapse, where Earth's magnetic field loses bite planet-wide? We can't confirm it, but for now, as we zoom out from Earth's fiery core and the invisible shield it produces, it's time to take a deep breath and marvel at what we've uncovered. From the molten dance of iron at the heart of our planet, to the shimmering auroras that dance at our poles, Earth's magnetic field is more than just a scientific curiosity. It's our planet's silent superhero. Throughout history, it has flipped, shifted, and wobbled, but never once disappeared. It has guided migrations, protected our precious atmosphere, and shielded all life from solar chaos. As we look toward the future, the timeline for change is comfortably vast. The inner core continues to grow at just about 1 millimeter per year, so slow it's like watching a mountain form in slow motion. Billions of years will pass before any real danger arises from that alone, so don't worry, we're not about to lose our force field anytime soon. Scientists around the globe are pushing deeper into the mystery, studying ancient rocks in places like Canada, Australia, and South Africa. These rocks act like tiny time capsules, helping us decode Earth's magnetic past and offering clues about whether other planets might have their own protective shields. And by studying our magnetic field, we don't just learn about Earth, we also tap into the secrets of life itself. We begin to understand why we exist, how our planet has remained so uniquely habitable, and whether distant exoplanets might also cradle life beneath their own magnetic cocoons. It's wild, right? The story of our magnetic field isn't just about iron and magnetism, it's about survival, evolution, and maybe even aliens. So, to wrap this up in a magnetic bow, Earth's field is old, bold, and beautifully dynamic. It may flip again, it may wobble some more, but it has never failed us. It's the invisible hand that has always had our back. If your brain is still buzzing with electromagnetic excitement, don't just sit there, subscribe, drop a comment, hit that like button, and share this video with someone who loves space, science, or just cool invisible stuff. Who knew a field you can't even see could be this dramatic? See you next time, space travelers. Stay grounded, stay curious, and keep looking up.